In this lecture, we will study string matching algorithms. So, what is the input? The input is an array A, array T of length n, which is the text, and we are also given a pattern P of length m, and we need to find if this pattern P is present in the text T or not. So, what do you mean by present? That means there exists an index S such that Ts plus 1 to Ts plus m is exactly equal to P1 to m. So, this is a very fundamental problem. All editors you can think about, like Notepad or any editor, you can do a find, Control F, and you can type any string, and it searches in the text whether the pattern is present or not. Okay, so we will follow our usual algorithm design technique. So whenever we are presented a problem, we will first look at the most obvious algorithm. So here the most obvious algorithm that one may think of, let's call it naive matcher, which simply tries for all possible S and tries to match from S plus 1, tries to match the m length pattern in the text from S plus 1. So it simply runs a for loop from S equal to 0 to n minus 1 and simply checks whether the pattern P1 to m exactly matches with T S plus 1 to m. And if it finds a match, then it returns then it returns S plus 1 where the match was found. And if there is no match, or then if after exiting the for loop if it did not return during the for loop, that means that there is no match, and in this case it returns 0, which indicates that there is no match. Okay, so what is the time complexity of this naive matcher? This naive matcher runs this for loop, which runs for order n minus m iterations, and for every S, it's try to match a pattern P of length m, which takes order m time, which takes order m time. So the time complexity of this naive matcher is order m times n minus m. Okay. Now you see that this time complexity can be substantially improved upon. So this time complexity is a quadratic time complexity. So we will see an algorithm which does this job in order n time. But before that, let's first understand why or where lies the scope for improvement for this naive matcher. So to understand this, you see that the naive matcher does not utilize partial matches. So let's consider this example. Suppose this text T is a sequence of 0, 0, 1, and the pattern that we are looking for is 0, 0, 0, 1. So the naive matcher starts to match from the first character of T, and it could not match, so it was 0, 0, 1, and then again in the second iteration it tries to match from the second character. Now that is unnecessary because it knows that the third character is 1. Because this 1 is there, and whereas the first 3 characters of P are 3 zeros, so these partial matches, it is not able to use this information. So we will see how this Knuth modis Pratt algorithm successfully or efficiently uses this information and it implements this string matching task in order n time. So the idea is to pre-compute the information available in these partial matches in a function pi called prefix function. So pi is a mapping from 1 to m to 0, 1 to m minus 1. And how is it defined? So for q in 1 to m, pi q is defined to be the length of the longest strict prefix of p1 to q, which is also a suffix of p1 to q. So let's understand this definition more clearly using this picture. So when computing pi q, I will only focus on the first q characters of the pattern. So pi is a function of the pattern. It does not depend on the input text. Okay. So when I am computing pi q, I look at the first q characters of p, the pattern, and look what is the longest strict prefix. What do you mean by strict prefix? That means the entire string is also a valid prefix, but that means the string from 1 to p1 to pq is also a valid prefix, but that is not a strict prefix. So a strict prefix is a prefix which is not equal to the string. So I look for a strict prefix p1 to q which matches exactly with the suffix of p1 to q. That means the first k characters of p matches exactly the last k characters of q of p in and I am only focusing on the first q characters. I am not looking at the entire p. P contains m characters, and there can be characters here also. So maybe p is a big pattern string, but while computing pi q, I only concentrate on first q characters of p. Okay, and I look for all possible k. Definitely, if I pick k equal to 0, then I have empty prefix, and empty prefix clearly matches with empty suffix. So this set k equal to 0 is always satisfied, and I look for all possible k's from 0 to q minus 1 and take the maximum. That will be the length of the longest strict prefix of p1 to q, which is also a suffix of p1 to q. So by definition, we can see that pi q is strictly less than q because k has to be strictly less than q because of strict prefix. We are working with strict prefix, and pi 1 is 0 because if q equal to 1, then pi 1 has to be strictly less than 1, and the only k that is available while computing pi 1 is 0. So here is an example. So suppose let's look at this pattern p0001, and pi 1 is 0, pi 2 is, I have to look at the first characters of p, and there what is the length of the longest prefix that is also a suffix of the first two characters of p. That way pi 2 is 1, pi 3 is 2, and pi 4 is again 0. Now let's understand the KMP matcher. So it computes the prefix function by calling an appropriate function. We will see that this job can be done in order m time. So this takes order m time. We will see. Okay. And then we try to match this pattern p. We read one character at a time from p and try to match this pattern p with t, and we maintain an index q which is like till what length the pattern p has already matched. So to begin with, q is 0, and I, the integer I is the index where the character I always points to the character in the text t that I am currently reading. So I have a for loop in n iterations. I will read n characters. So first I will see that I have already matched the first q. So remember what is q? Q is the partial match. I have already matched the first q characters of p with I minus 1, and I am seeing can I continue this partial match into a full match. So while q equal to 0, q greater than 0, can I extend this partial match? That means if pq plus 1 equal to ti, that means I can extend. On the other hand, if pq plus 1 is not equal to ti, that means this partial match I cannot extend. And in the knife algorithm, in the knife string matcher, I was throwing this partial match, but here I should not be throwing, because I know that first q characters has matched. So first q characters has matched, that means that the next if for a fresh start of the matching, these pi q characters, the first pi q characters is already matched, because pi q is the length of the longest prefix, which is also a suffix of first q characters of the pattern p, and the first q characters has already matched. So I write q equal to pi q, and again assume that the first q characters have been matched, and again I try to continue my matching whether the next character pq plus 1 is equal to ti or not. So this way, if q becomes 0, that means that no partial matching is available, and I have to again start from scratch, and that's when I will exit from the while loop. Or other way, I can exit from the while loop if I find a match and I see that it is possible to extend this partial match by one character. I can include this ti into my partial match, and that is checked in the next if condition, that if pq plus 1 is equal to ti, then the next character has also matched, and so before first q characters has matched, now the q plus 1th character of the pattern also matches the ith character of the text. So now we have q equal to q plus 1. Of course, if q equal to m, then we have found a successful match of the entire pattern, and that the starting point is I minus m plus 1. It is that the pattern ends at qth index and its length is m, so that pattern should have started at I minus m plus 1. So the pattern has ended at this index I in this case. So okay, so it is not at all clear why this takes order ending. On the contrary, it looks like that it takes this for loop runs for order n times, but this while loop can run for order m time. But we will show that the total number of iterations that this while loop runs across the entire algorithm. So this while loop is entered, the while loop may be entered in various iterations of for loop. Maybe in the first iteration of for loop, this while loop iterates over say 0 iterations. Maybe in 10th iteration of for loop, this while loop iterates for 5 iterations, and so on. And you sum up all these numbers, and we will show that the total number of iterations that the while loop can make is at most 10. Okay, so you do this computation for this while loop separately, the time taken in the while loop entire throughout the run of the algorithm, that you compute separately and show that time is order n. And if you leave the while loop, then this for loop takes order n time, because the body of the for loop except the while loop takes order 1 time and it runs for n iterations. So here is how we proceed. The for loop runs for order n iterations, and we will show that the inner while loop runs for order n iterations in total. It can happen that once there is one iteration of for loop where this while loop runs for say n by 10 iterations, but then that we will show that somehow if it runs for more number of iterations once, then it will run for less iterations in some other iterations of for loop, because we will show that the total number of iterations that the while loop can run is order n. We will show actually stronger, we will show that it can be at most n. So here is few observations. So observe that we already observed that pi q is strictly less than q. Why? It again, let's recall, it simply follows from definition. What is pi q? It is the length of the longest strict prefix of p1 to q, which is also a suffix of p1 to q. So prefix of length q is not allowed here because we are looking for strict prefix. That's why pi q is strictly less than q, and that implies that q continually decreases in the while loop. So if you go to the while loop, the body of the while loop contains exactly one statement, which is q equal to pi q, and because pi q is strictly less than q, that means that q continuously decreases in the while loop. Okay, and also q can never go to negative. So by the definition, q is only assigned to pi q, and it strictly decreases, and for the definition pi q is always a non-negative number. So q is never negative. It was started with 0, and when q is increasing, so you see that q increases only in the first if statement, and that means that q can increase by at most 1 in every iteration of for loop, which runs for order n iterations. So this while loop decreases q, this if condition increases q, and if q starts with 0, q increases by at most 1 in every iteration of the for loop, and hence and q cannot become negative. So if you sum the sum of all decreases of q across all the iterations of while loop, that is at most n. So this you can think of q is the amount of money you have. Suppose on day you start at day 0 you don't have any money, and every day you can earn at most 1. That is analogous to increasing q by at most 1 in every iteration of for loop. So every day you earn at most 1, and in the while loop you are spending some time. That means when you are spending, that means q drops, and because you are earning at most 1 rupee every day. So in the n days, that means corresponding to the n iterations of the for loop, you can earn in total n rupees, and hence the total spending you can do is also is at most n. Okay, and the spending is that when you are spending, you are decreasing q, which is analogous to you are decreasing q in the while. Okay, so this shows that the total decrease of q is at most n, and while loop, in every iteration of while loop, q must decrease. So the number of iterations that the while loop runs throughout the run of the algorithm is order n, is at most n. So now we only need to show. So this shows that the this for loop and this while loop, this part of the computation in the Knuth Morris Pratt algorithm takes order n time. Now let's see the compute prefix function algorithm, and it is exactly the same algorithm like KMP matcher. It is like simply matching p with itself. Okay, and using the same argument you can show that it takes order m time. So let's just see the algorithm. So again it initializes pi 1 to 0 and k equal to 0. K is the length of the longest prefix that has been matched yet. Okay. And then we are running a loop for q equal to 2 to m. We will simply in the qth iteration we will compute the value of pi q, and again we are using k that currently, if I look at at the qth iteration, I have already computed the values of pi 1 to pi q minus 1. And k is what? I will ensure that k is pi q minus 1. That means it is the length of the longest prefix of p1 to q minus 1, which is also a suffix of p1 to q minus 1. Okay, and then again I will do the same thing. I'll check whether this partial match of the prefix with the suffix can be extended. So what is the next character of the prefix? The prefix length was k. So I am seeing whether pk plus 1 is equal to pq. Okay, then I can extend, and I don't need to go into the while loop. I come to the if condition and I increase k, and then I update pi q. Otherwise, if I can't extend, then I go what is the next k that I have to look at. I have to look at the next k is pi k, and I update k equal to pi k. And again you can do the same argument that this for loop runs for m iterations, m minus 1 iterations, and then the total number of iterations that the while loop runs is again at most m, because again k starts with 0 and k decreases strictly in this while loop, and k can increase by at most 1 in this for loop, in this if condition, and hence the total decrease in the while loop can be at most m, and thus the number of iterations that the while loop runs is also at most m. Okay, so what is the total time complexity of KMP matcher? Order n time for this for loop and while loop, and order m time for computing the prefix function. So total time taken is order n plus m. Now m is less than equal to m. N, this equality is because m is less than equal to n, because if n is more than n, then you know that this pattern cannot be present, and hence you simply output no. So because m is less than equal to n, order n plus m is also can be written as order n. Okay, so I would request you to not look at the compute prefix function first, because the idea is basically matching the string with itself. When you are doing it for the first time, when you are reading this Knuth Morris Pratt algorithm, this is a very beautiful algorithm. When you are reading it for the first time, you assume that this prefix function can be computed in order m time, and then you first understand this KMP matcher with the analysis. Once you feel that you are confident with your understanding of this KMP matcher, then you go and the same idea is used while computing the prefix function. Okay.